Morgen, I'm Andreas Winter. I'm charged by Christian Deppe to introduce the speaker of the morning. So obviously we are here for the Symposium in memory of Rudolf Ahlswede. We are happy that Charles Bennet could make it over here. He will speak about quantum information and ideas that you get from quantum information about irreversibility and information loss. Charles Bennet, to those of you who don't know him, is regarded as one of the founding fathers of quantum information theory at all, of reversible computation, of the whole field of the physics of information. And with that, it's a pleasure to introduce him, and we are waiting for your lecture.
Good to be back in Germany where people do this. It's also handy when you have a grandchild in one hand, because then you can't applaud, but you can just do this. This is dedicated to Rudolf Ahlswede. I didn't know him very well. I think I met him maybe only once or twice. And about a year and a half ago, I tried to interest him in the excitement of quantum information, in rebuilding information theory on quantum foundations, and he needed no propaganda talk. He realized this was very exciting, and he said, "Oh, you only wish he had been able to begin working on this many years earlier." This contrasts, I think, with a similar experience I had with another recently deceased person from the information theory, which is Ray Solomonoff, who is one of the founders of algorithmic information theory. And when I tried to get him interested in quantum information, he said, "Oh, there's too much to do in ordinary classical information for me to want to worry about that." I'm going to talk about quantum information, and not from a very technical standpoint, but from trying to draw in people from other scientific disciplines, or maybe even just show why it should be interesting even to a lay audience. Fortunately, information is not an idea that needs to be explained to anyone. We're in the middle of an information revolution, so practitioners of information theory don't need to explain things like source and channel coding to the general public. They already know about that when they want to transmit information over their modem cable or their wireless connection, or they want to compress their disk because it's getting too full of multiple copies of the same file. But if you ask what information is, it's really a very successful abstraction of the notion of distinguishability considered separately from the physical medium that the information is carried by. And this abstraction leads to, this is somewhat an abuse of the word fungible, which is normally used in economics. But in this sense, the fact that bits can be divorced from their carrier makes possible Moore's law, and the bits become more and more useful as they become smaller and cheaper, unlike shoes. So by ignoring these irrelevant physical properties of information, we can get a very powerful theory, which is more powerful than if we thought of information as it once was thought of, as the manipulation of abacus beads or pebbles. This is a pretty old abstraction. I think it certainly went back to the days of Leibniz and Boole, if not before that. However, I think that in the 20th century, when the laws of computation and information were really codified, the abstraction went too far. Some physical properties of information carriers began to be ignored or abstracted away. But there are some physical facts that you really can't ignore. You cannot transmit information faster than the speed of light. And it's often said that you can erase information when you don't want it anymore, and you can copy it without disturbing it. Well, these are not entirely true. Well, this one is true. When you erase information, it generally costs some work to do that. And finally, this question of copying highlights the difference between classical and quantum information. So the kind of distinguishability that physical objects, bodies have, is not quite that simple, clean-cut thing that I showed before. So physicists and chemists, of course, developed quantum theory in the early 20th century, and they didn't think it was a theory of information. They thought it was a theory of molecules and atoms and particles. But if you'd asked them what was the status of distinguishability of the states of these things, they would have said, well, you cannot read or copy the state of an atom without disturbing it, and you can have two atoms or two photons in a kind of state in which the correlation between them is too strong to be explained by some common history, and on the other hand, not strong enough to be able to use it to send a message faster than light or backward in time. So these were some important differences of the way physical distinguishability behaves from that abstract model. But there's also some important similarities, and that is that the transformations of quantum states can all be boiled down to a very simple primitive. Just as in the classical information processing, any quantum state can be described in terms of a number of two-state quantum systems, and then any transformation you need to do on that can be done by operating on these so-called qubits, 1 and 2 at a time. And these are fungible among different quantum systems. So this means that it's possible to rebuild the classical theory of information processing to include these quantum features that were originally absent and still keep it a very abstract theory that doesn't talk about electrons or photons or anything of that sort in an essential way. So what this says is that if we take this somewhat older theory of quantum mechanics and apply it to information, which was originally described in these classical idealized terms. When I say classical, I mean in the sense of classical physics. We get this larger subject of quantum information. And of course, information technology only sticks out a little bit into this quantum part. There are very few applications as of yet of this quantum information. But it is conceptually elegant in the sense that it's a generalization. I often compare this generalization to the generalization from real numbers to complex numbers. Complex numbers would be beautiful even if there wasn't any particular use for them. And indeed, some questions involving real numbers are easier to answer because you use complex numbers in the process of answering them. And then similarly, we have, well, that's a rough analogy, some computation involving only bits can be done more efficiently if you allow quantum information in the intermediate stages of processing. Well, as I said, quantum information is mainly famous because it will speed up some hard computations and it allows new kinds of cryptography and communication. But I'm going to mainly talk about trying to get an intuitive grasp for quantum information. And also, if you think about it, it can help explain the origin of randomness and our state of imperfect knowledge of the past and future. Of course, randomness is pretty important for information theorists. There would be not very much to do without noise in information theory. So it's a sort of philosophically interesting to wonder where this noise comes from. Well, let's look into this notion of the past and the future. In the worldview of classical physics, it seems that information cannot be created or destroyed, that the future and the past are entirely determined by the present. What you might call a superficial understanding of quantum mechanics seems to produce a very different picture. There are things that are absolutely unpredictable, like whether a particular radioactive atom will decay. And then on the other hand, the past seems to behave in a very different way. Whatever has happened, and it may be that it seems to be definite and unambiguous. Of course, there's some tenuous or sort of halfway events, maybe they don't deserve to be called events, in the past, which are ambiguous perhaps in the same way as the future. That is not because they are because of any ignorance of them, but because they're ill-defined. I'll give an example of this in terms of a Mach-Zehnder interferometer. So this is an apparatus in which we have a half-silvered mirror here, and another one here, and a couple of ordinary mirrors, and the path lengths are arranged to be equal along this path here and this path here. And when you build this equipment, if you build it carefully enough, and you send a light beam in here, or even a single photon, you will find that the photon has half a chance of going this way and half a chance of going this way. And when it comes to this second mirror here, instead of what you would expect, it would half come out here and half here, it all comes out in one direction. If you change the path lengths a little bit, it will all come out the other direction. So the quantum explanation of this is that when the photon is in the middle of this equipment, if you are not observing where it's going both paths. And after the experiment is over, even God doesn't remember which path it followed. Now that's a sort of religious way of talking. I got this idea from Danny Greenberger. And he said, well, as far as he's concerned, any God who would want to know which path it followed, he wouldn't believe in that God. So now I'll get to a more mathematical way of describing quantum information in a moment, but suppose you're trying to explain it to people at a dinner party. Well, everybody knows what information is, but quantum information is more like the information in a dream. And if you try to describe your dream, eventually you forget the dream and remember what you said about it. You can repeat that as often as you want. And you can't prove to someone else what you dreamed, and you can lie about it. Sometimes I have a little trouble lying about my dreams to my wife, but I think that's a non-quantum effect. But unlike dreams, quantum information obeys some well-known laws. And here they are in more mathematical terms. How many mathematicians do we have here? People who are trained in mathematics. How many people know what a vector space is? All right, about half. Do we have any physicists? No. Okay. Well, okay. So then I'm at the right. Some of you may want to ignore this. Okay, so these are the laws that establish a correspondence with quantum mechanics as a physical theory. That is, it takes a mathematical formalism and connects it to physics. And it says that to every physical system, there is a space of dimensionality equal to its maximum number of reliably distinguishable states. Now, I think some mathematicians would imagine that Hilbert spaces always have infinite dimension, but there are also finite dimensional ones. And every direction in that space corresponds to a possible state, and the spontaneous evolution of the system is just a rigid rotation in that space. And then there's some other laws that I'll sort of skip through. But the most basic law is this one. That is, between any two reliably distinguishable states, and I'll give you an example here, there are other states, a continuum of other ones, that cannot, in principle, be reliably distinguished from either original state. For example, if these were vertical and horizontal polarizations of a photon, these would be diagonal. I think this thing emits polarized photons. I don't know if I've got a polarizing filter here, but a piece of glass will do. Do we have just an ordinary glass? A drinking glass? I don't really need to show whether this laser is polarized. I believe it is. Okay, so here we have photons that can be prepared in the polarization is always some direction perpendicular to the direction of travel. So they can be horizontal or vertical, and these two can be reliably distinguished by an apparatus like a sufficiently asymmetric crystal and two detectors. So the vertical photons are deviated as they pass through the crystal, and the horizontal ones are not. If you give them something polarized at an intermediate angle, instead of being deviated by an intermediate amount, they decide probabilistically whether to become horizontal or vertical. So this intermediate state is represented in the formalism by just this intermediate vector that is this linear combination of the two vertical and horizontal, and you can also have the intermediate combination of the other sign. So these two states are reliably distinguishable from each other because the directions are orthogonal. But this and that are not reliably distinguishable because those directions are not perpendicular, and that means this behaves somewhat like this always, and which is the basis of quantum cryptography. So my colleague, Professor Bill Wooters, had a nice analogy for this, how a quantum system behaves when you try to measure it, he says it's like one of those old-fashioned schools where the teacher will confront the pupil and say, are you a vertical or horizontal? And the pupil starts saying, oh, I'm polarized about a 55-degree angle from the... I believe I asked you a question. Are you vertical or horizontal? Horizontal, sir. Have you ever had any other polarization? No, sir, I was always horizontal. So that's one description of the way a quantum system behaves when you cause it to interact with the measuring apparatus. I'm going to go back over that description and look at it in a more sophisticated or a more subtle way later on. But this is what you might say the Copenhagen view of quantum measurement. So I said that there is a similarity to classical information processing because any processing of quantum data can be done by 1 and 2-bit qubit operations. And so we can imagine, just as you can imagine a classical computer circuit diagram as having wires that carry bits and gates that act on the bits, and then you get out some output, which is a function of the input. In a quantum computer, these wires would carry qubits, for example, polarized photons, and the gates would be some interactions between two of the qubits or operations on one of them. Now, an operation on one qubit is simply just a rotation of the polarization. An example of a 2-qubit operation is this quantum exclusive OR, or controlled NOT. So what that says is that if we have two standard states of the photon, I'm going to color one yellow so we don't get them mixed up, and we'll call the vertical photon a representation of a 1, and the horizontal one the representation of a 0. And these quantum states are conventionally enclosed in half-angle brackets, a notation originated by Dirac. So here's an example of a quantum gate. It's the quantum analog of the exclusive OR, which is to say that we have two inputs to it, the control input and the target input. And the control input is not changed, but the target input is flipped to the perpendicular state from its original state. It's rotated 90 degrees. If the control is 1, but if the control is 0, it is not changed at all. So this is a very simple quantum analog of a simple classical data processing operation, such as you would use in a one-time pad encryption, for example. But because it's a quantum operation, the superposition of inputs gives a superposition of outputs. And so that means if I put the control in this diagonal state, which is represented as the linear combination of horizontal and vertical, then what comes out has to be the superposition. That is, the superposition is the physicist's word for linear combination. The state, it is intermediate between these two states in 4-dimensional space. So that looks like that, at least algebraically it looks like that. And this is the state that has the quantum property of entanglement, which I'm going to talk about now, which is something that is somewhat hard to explain. It makes perfect sense if you can think in 4-dimensional or higher space, but that's a little hard to explain at a dinner party. So I'll get back to entanglement in a moment, but so we said I wanted to express classical data processing in quantum terms. Well, that means I want to say what a classical bit is. Well, it's just a qubit with one of two standard values, like vertical and horizontal. And a classical wire is something that carries those faithfully, but may randomize superpositions of them. And why does this randomization occur? Well, this has very much to do with cryptography. It occurs because the quantum data in passing through the wire in general interacts with its environment. And the environment will learn the value of the data if it was one of these two orthogonal states, and otherwise it'll become entangled with it. So I use this blue shading to represent entanglement. So if I have, what I'm saying is that whenever I have a classical wire, what's really going on is quantum data is flowing through, but it's interacting with an environment in such a way that the environment is trying to learn whether it's 0 or 1. If it was 0 or 1, the environment learns. If it was anything else, it becomes entangled. And in any case, the environment escapes from our control, and what comes out here is either unaltered if what was going in was 0 or 1, or it looks as if it's been randomized. It is randomized. And that means that a classical channel is just a quantum channel with an eavesdropper, and a classical computer is a quantum computer that is handicapped by having eavesdroppers on all its wires. As I said, these quantum computers are of great interest because if you could build one, it could solve some hard problems, such as factoring. Here's an example of a fairly hard factoring problem, which was solved, I think, over a period of months on many computers. By contrast, the reverse problem of multiplication is much easier. In fact, you don't even need a computer to do it. You can say 7 times 3 is 21. That's where that 1 comes from. We carry the 2, and then we got another 3 times 7. So if you had a lot of paper and a quiet weekend, you could do that without a computer. But with a computer, it's a lot of work. Now, in an ordinary computer, you need to keep information from leaking into the computer and randomizing the data while you're working on it. And that's the whole point of constructing reliable computers, which we're pretty good at now. But in a quantum computer, you have to also keep information from leaking out. And if you can do that, and you are thereby able to allow the computer to remain in entangled intermediate states, then the process of factoring is not much more difficult than the process of multiplication. So this is an example of a computation whose privacy, but whose efficiency is handicapped by eavesdropping. Now, people often try to understand the difference between classical and quantum data processing. And I guess it was some evening I was working on this, trying to explain it, and I hadn't eaten anything for a long time, so I was pretty hungry. And I began thinking in gastroenterological terms. And so I would say, well, the thing about a quantum computer, it has a narrow input and a narrow output, just like a classical computer. You put a classical computer in, n-bit input, n-bit intermediate state, n-bit output. In a quantum computer, the input and the output are narrow also, but the intermediate state can be has this very large Hilbert space to rotate in. It has a space of 2 times 2 to the n minus 2 dimensions, which is a lot of room for maneuvering. And so there's an expectation, or at least the opportunity, for a quantum computer to do some kinds of processing faster than a classical computer. Then here's another, perhaps more relevant to an information theorist way of comparing. People often say, well, it's actually a bad question. How much information is contained in n qubits compared to n classical bits or n analog variables? Isn't really a qubit something like an analog variable that can be in between 0 and 1? Well, no, not because of entanglement, because if I have n qubits, that's a system with 2 to the n reliably distinguishable states. And therefore, the totality of all states of that system lives in a 2 to the 2n dimensional space. So the amount of information required to specify the state is enormous, much greater than an analog variable, and certainly greater than a classical digital variable. But the amount of information you can get out is only n bits, just as if it were a classical digital variable. So it's really quite unlike an analog variable. And another way it's unlike an analog variable is that there is good error correction for quantum data and good error correction for discrete classical digital data, and there isn't good error correction for analog data. So that when we talk about the overall usefulness of these three kinds of data, we come to a situation where digital and analog computation are approximately equally powerful. Now, at one point there was a thought that analog computation would be more powerful, but it isn't, because you can't make an analog computer very reliable against environmental disturbance. Now, why am I saying that analog computation is about as powerful as digital? Well, the reason is that all of our analog computers are actually, all of our digital computers are analog computers in which we use certain ranges of voltages, say, to represent 1 and 0. So these two, all of our computers, like this one here, are really analog circuits which are designed to operate in a digital mode. So these two are about equally powerful, and this is more powerful. Well, I wanted to go back to speak of entanglement. So here we have this state that's between both photons being horizontal and both vertical. If you work out the algebra, that's the same as between both being 45 and both being 135 degrees. And it is not the same as each of them being in a state of its own. And this is a pretty simple piece of algebra, but if you want to talk about it to somebody who doesn't like to think or is not comfortable with algebra, you can say that the photons are in a definite state of sameness of polarization, even though neither one has a polarization of its own. So an entangled system then can have zero entropy, even though the parts of it have a lot of entropy, can have even maximal entropy. In the lab, the way this behaves is you create a pair of these photons, and if you measure either one along any axis, you always get a random result. For example, it might turn out to be vertical. And if you do that, then the other one also turns out to be vertical. So then you'll say, well, why is this happening? The first shot at an explanation is that this source really is not zero entropy. It's emitting something that is probabilistically distributed over different angles, but always emits two photons at the same angle. And then you fire it again, might emit two photons at a different angle, but the same in both cases. But that explanation doesn't work because if it were emitting, say, two diagonal photons and you were measuring the vertical horizontal, you would sometimes get them behaving differently, and yet they always behave the same. So this is a sort of a toy version of what's called the proof of Bell's inequality, which is that you can't explain the behavior of the photons by assuming that they have some distribution of classically, a correlated distribution of individual states. Now, how do you explain it? Well, I just explained it by instantaneous action at a distance. When this photon becomes vertical, it causes this one to become vertical. But that doesn't make a lot of sense because it contradicts relativity. It's faster than light communication. Besides, how would you know where to send the message to? This photon might have bounced off a mirror and gone in some unknown direction. Of course, the right answer comes from quantum mechanics. If you think in terms of four-dimensional space, you get the right answer. But if you don't like to do that, you can say, well, whenever we measure something, an entangled state, suppose this is time is going this way and space is this way. It comes up here, passes through a vertical filter, so it decides it was vertical. In fact, it decides it always was vertical, and therefore its twin is vertical, and whenever you measure that, it comes out vertical. Now that's a sort of science fiction-y type of explanation, because we know there can't be messages backward in time. But a message backward in time actually, well, it's not really a message. That's the thing. You can't call something a message if you can't control it. So a message backward in time is okay to think about, either if the sender cannot control the message, which is the case of entanglement, or if the receiver ignores the message. So I'm trying to give you now some more metaphors for this entanglement. Most states of a composite quantum system containing two or more particles, or particles with two or more states each, are entangled, and that is a state of the whole that behaves in ways that can't be explained by imagining that each part has a state. Now, this was an idea that was a little easier for me to explain, although I never tried to do it at the time, back in 1967 in the Summer of Love in San Francisco, when there were a lot of people sort of like these ones here. So those people would have thought that it makes perfect sense for two people to be perfectly attuned to each other, even though each one has no opinion about anything. Now, they were not very mathematical, and they thought that with enough LSD, everybody could be perfectly in tune with everybody else. But now that we have a quantitative theory of entanglement, we know that it is monogamous. The more entangled two systems are with each other, the less entangled they can be with anything else. So let's see to understand this property a little better. So as I said, if A and B are perfectly entangled with each other, so they have maximum correlation allowed by quantum mechanics, they cannot even be classically correlated with anything else. And if one of the particles tries to share his entanglement with a third party, or lets it get eavesdropped on, then this entanglement will be degraded into mere classical correlation. So let's take this circuit that I showed you before that produces an entangled state. What this means is that in this state, if we measure this photon and this photon along the same axis, they will always agree. So that once each one will behave randomly, but the other one will behave in exactly the same way if I measure it the same way. Well, now let's let this guy try to pass on, share this entanglement. Let's try to make a third identical copy. And we do the same thing and let this escape into the environment. Then what will happen is that these two will only be classically correlated. That is, if there will be an axis along which if you measure them they will agree, but along other axes they won't agree. So the perfection of their bipartite correlation will have been degraded. And this always happens if you try to share entanglement. So let's go back to this analog of this pedagogical analog of measurement from Bill Wooters. Let's watch these photons behave randomly and see if we can understand that in terms of entanglement. So as I said, they'll behave randomly, but let's say we're going to try to undo a measurement. So what I'm saying is let these photons be split into two separate beams, but let no one observe them. And then maybe even to speak of them and behaving randomly is not quite the right way of thinking. And indeed, this splitting can be undone by putting in this is essentially one qubit operation. It rotates the light 90 degrees. You can do that with a thin plate of anisotropic material. And then put another copy of the calcite crystal of the same thickness behind it. And what we get is that the two will be combined into a single beam. This is just a polarization version of the interferometer I showed you before. So what happens is to say that these photons probabilistically decided which beam to go into and then went back into a single beam is not right. They didn't decide some to go here and some to go there. They entered in an entangled state in which their state of polarization was entangled with which beam they were in. And then this entangled state, which still had no entropy to it, was maneuvered back into the original state that went in by a process that's entirely reversible. So what does this mean when we say the photons behave randomly? Essentially what we're saying here is that if I measure it with something like a photon detector, I'm producing a lot of witnesses as to whether the photon was in this beam or that beam. A lot of different particles have witnessed it. And in terms of the schoolroom, what really makes the photon forget his original polarization is the embarrassment of having to answer the question in front of the whole class. To become a little bit more mathematical, I spoke of quantum states as directions in Hilbert space. And now that was really speaking of states that have no randomness to them, no entropy. That's similarly to exact mechanical states of a mechanical system. But of course, people deal with probability distributions of states, states which have some ignorance. And in the quantum mechanics, a very useful notion is the notion of a mixed state, which describes two seemingly different things. That is a probabilistic ensemble in which this system might be in one of several states with different probabilities, and a situation when the system is entangled and there's some other part of the system which we have no access to. So the system we care about is a system A, but it's part of a larger system which is in a pure state. And in an open system, pure states can evolve to mixed states. Now, this may seem like a kind of arbitrary representation of probabilism in quantum mechanics, because you would say, well, when I just, well, I haven't said what the density matrix is, actually. I haven't said that it's an arbitrary notation, but it's Did I say what it is? Yeah, here's the density matrix. We take the projector onto this state, and we multiply it by the probability, and we add them up over all the states. Or in the case of a subsystem, we take the trace of this density matrix, or this bipartite system over one of the subsystems. Different ensembles can have the same density matrix. For example, any equal mixture of two orthogonal states has this density matrix. And so what common feature of it does the density matrix represent? In other words, different ensembles are represented by this same quantum notation. So that sounds like it's a bad thing because I'm confusing different things by the same name. But it's actually good notation because this density matrix represents all and only the information that can be obtained by sampling the ensemble repeatedly or by observing the A part of the compound system. And ensembles with the same density matrix are indistinguishable, and pure states with the same density matrix for the A part are indistinguishable if you're only allowed to observe the A part. Moreover, there's this theorem which was discovered by a whole sequence of modest people, beginning with Schrödinger, who also said somebody must have discovered it before, which is that if we have a system in a pure state, then for any ensemble compatible with that pure state, there is a measurement that Bob can do on his subsystem alone without Alice's permission that remotely generates that ensemble in her lab, in the sense that for each member of the ensemble, Bob will get that outcome I with probability p sub I. And if that happens, he can't control it, but if it happens, he knows that what's left in Alice's lab is this pure state psi sub I. Now, Schrödinger called this steering, but that's a bad name for it because Bob cannot control what Alice gets. He merely just finds out about it. I tried to explain this steering to my automobile insurance company. I said that I had that kind of steering, and they said they would cancel my insurance. So this is the thing about entanglement that is understanding this or appreciating it is the thing that makes it so different from classical intuition. That and the equivalent fact that a pure whole can have impure parts. And my colleague John Smolin has given this viewpoint the nickname the Church of the Larger Hilbert Space. And this is the habit of always thinking of a mixed state as a pure state of a larger system, and of any probabilistic evolution as being a deterministic evolution of a larger system. And because of the way quantum mechanics behaves, no one can prevent us from thinking this way, and we find it satisfying and helpful to our intuition. As you can see, I'm a believer of this church. So this only makes sense in the quantum context because there a pure whole can have impure parts. Now, of course, this is an idea that's pretty much foreign to most, perhaps all religions, pre-20th century religions, certainly to Christianity. So this now raises again the question, if this is the way information works, how does it seem so different to us in the classical world? Why does it seem that things are in definite places and everybody can know about them, and these superpositions and entanglement are so hard to observe that they were not even observed until the 20th century? And there are various explanations of this. They're probably the most successful goes under the general name of a decoherence theory, and a particular brand of decoherence theory that I find particularly attractive is called quantum Darwinism. Although I think that it's a bad name for it. It was a name originated by Wojciech Zurek. I think a better name for it would be quantum spam, as you'll see why in a moment. So the idea is here, at least in some situations, a quantum evolution consists of a system interacting with its environment. And the environment has many parts which interact independently with the system. That is, they interact more with the system than with each other. And the result of this interaction, of course, because it's a quantum evolution, is an entangled state of the whole multipartite system. And in particular, if I ask how does the system correlate it with the entirety of the environment, it's perfectly entangled with the environment. So if I measure the system along any axis, I can find out about that exactly by observing the whole environment. However, because this environment has many parts, if I just say, how is the system correlated with part of the environment, there will be a preferred axis on which it's correlated, and then in other axes, it will appear to be independent of the environment. So this is a manifestation, really, of the monogamy of entanglement. So I'm entangled with the entirety of the environment, but I'm not entangled independently with the separate parts. However, I can be classically correlated with the separate parts. Zurich called it Darwinism because he says there's a preferred basis in which information, a preferred axis in which information proliferates. But it's not due to being able to reproduce faster. It's more due to its being copied many times in that basis. So that's why I call it spam rather than Darwinism. And this is not true of all quantum evolutions, but it is true of those that we observe in the kind of environment that we live in, which is an environment that's not at thermal equilibrium and that has many systems that interact more strongly. The environment contains many subsystems that interact more strongly with the system in question than with each other. And I'm going to talk a lot about that kind of interaction. But first we'll have a little detour through society and politics. So nowadays, of course, there's a lot of public information or information that people might want to keep private that is recorded and becomes public. And there's two sides to this question. You don't want every aspect of your life eavesdropped on, but perhaps sometimes some eavesdropping is good. There's a lot of discussions about that. But it's I think especially in the context of the last few days, this idea that for citizens to be armed is good for society is a crazy idea. So I've long thought that everybody should carry a camera rather than a gun. And actually I always do carry a camera. And this is actually quite a widespread idea, at least outside the United States. Quite a number of years ago, I saw a billboard advertising CNN news company where they want everyone to be a photojournalist. Okay, so getting back to science, it seems that there are three levels of privacy. There's this quantum privacy, information that can best be thought of as just as a consequence of entanglement that is then later undone, and the information may be best thought of as never having existed because you never observed it while you had a chance. And then there's this classically private information. It's been amplified, but most people don't know it. And then public information, which is what politicians lie about. And this situation looks rather different from the ancient world, in which a lot of public information was eventually lost. Now it seems that if you put something up if you blog about it, it's there forever. And there are many of the ancient Greek writers whose works only survive in a fragmentary form, especially, I think the most renowned example is Sappho, whose almost all of her works are gone. But there are other examples in every culture. In fact, in China, the first emperor wanted to enhance his place in history by destroying previous history, and almost succeeded. But much of what he tried to erase was reconstructed. In Sappho's case, it was due to the fact that her dialect becoming obsolete. And this is actually I've been trying to find out more about this Karvaka philosophy in India. And this is one of these philosophies which died out, and we only know about it by the hostile writings of its opponents. But as best as we can gather from what they said about it, they didn't like it because it was sort of an early form of atheism or agnosticism. So let's see about what happens to information in our classical world. Here's some information. Well, I'm not talking about information that people want to say, but information that nobody cares about. And I've been a photographer for a long time, so back in 1965, I thought this was a very interesting pattern of cracks and craters in the layer of mud in a riverbed. So I took a picture of them, and then a few days later they were washed away. So the question, the sort of epistemological question is, if nobody had photographed them, would there be a physical record of these raindrops somewhere in the world? And it's tempting to believe, and I started off initially believing, that this is not lost. It just becomes spread out so much as to be irrecoverable in practice, but still recoverable in principle. And people often say this: when you burn a book, the information in the book isn't gone. It just spread out in a complicated way in the smoke and the ashes. And actually, they usually say smoke and ashes, but it would be more proper to also include the heat, that is the infrared photons that are emitted in the course of burning the book. Visible photons too. But could it be that every macroscopic phenomenon is still recorded in physical evidence, in principle, if not in practice? And my prejudice for believing this was because I was annoyed by this, I guess it's not a very prominent school of philosophy now, but the postmodernists who, I guess during a period that was called the Science Wars, asserted that the past, or maybe in the present, doesn't have an objective reality independent of human belief systems. Anyway, so this seemed to me to be arrogantly anthropocentric. So I really wanted all this information to exist in the past. However, thinking about it a little bit more, I became convinced that the Earth doesn't have enough storage capacity to keep it all. And that most of the information that we might choose to care about, not what we actually care about, but what most information that we can describe as macroscopic that once existed, is washed away by much larger entropy flow into and out of the Earth. Now, how do we estimate this? And we can do it in terms of the energy flow, which is about on the order of 300 watts per square meter. And converting that into entropy, we get about 10 to the 30th bits per square meter per year. And now we say, well, suppose we're trying to use the Earth as a kind of tape recorder to store a lot of information. What's the biggest tape recorder that we have on the Earth? It's probably the formation of lattice defects in newly formed rock in the mid-ocean ridges, and this is you can estimate what that capacity is about 10 kilometers thick times maybe on the order of 1 bit per cubic nanometer, and the rocks last for about 100 million years before they get melted down again. So when you multiply that all out, we get about 10 to the 22nd bits per square meter per year of recording capacity of the Earth, which isn't enough to save everything. So we have to imagine that a lot of this information is lost. And let's think about how it gets lost. Essentially it goes radiated away from the Earth in photons that that radiate out into the sky. And of course, it's a problem to catch up with this radiation because it's leaving at the speed of light. So this is the Wild West version of this problem. So let's say it looks like we've got a new level of privacy. We have this quantum information that never really existed, the classical information that's escaped, and then we have the ordinary classical information that's secret and maybe not recoverable by anybody, but it still exists in principle, and the public information. So let's consider some of these mysteries of the past and in which of these categories they belong. Well, there are no quantum ones. This is a tantalizing, classically secret one. This is almost certainly exists because gold is very resistant to corrosion. And so there are a lot of gold rings in the Venice Lagoon, and nobody knows where they are. And then some information where it's not known whether it is there or not. It may be recorded in some physical and unambiguous way, such as if they discover the bodies of any of these people, or it may be that has escaped. And then there's information that we can argue is almost certainly escaped. Well, now supposing we're trying to get rid of some evidence of a crime, like this labor leader from the United States in the 1975. Well, you'd want to make sure that you didn't save his body or even the ashes. And then, also important not to tell anyone about it, of course. And then also maybe you want to get rid of your own physical memory. And now, on the other hand, suppose we wanted to save some information. Not all information is lost. There's stuff that lasts for a long time. And well, suppose we wanted to save information. There are various reasons for doing it. And the way we would do it is that we would record it in some durable medium and then redundantly store it in a lot of places. So this is, of course, a big business for storing business records in robust form. So any particular piece of information we want to immortalize, we can, but there's too much of it to immortalize all of it. Now, suppose we wanted not to store all or most of the information, but let's say a sort of low-resolution version of all the classical information that's happening on the surface of the Earth. Let's say millisecond resolution of just a video of the surface of the Earth. If you work that out, that's around 10 to the 16th bits, which is considerably less than the geological capture rate. Now, you might be wondering, is this happening already automatically? Could it be that by digging up these rocks, you could find out a low-resolution picture of what happened to Jimmy Hoffa? Because essentially we're looking at a hash of everything that happened on the Earth. Well, if you understand the properties of hash functions, that's not so. Because the general property of a random mapping of classical data or of quantum data is that if you recover a minority share of the output, it tells you almost nothing about a minority share of the input. So the only way in which this kind of video surveillance would happen is if someone is actually trying to make it happen. Well, what about getting the information back by having it reflected back? Say, well, that's certainly possible. You could do it. People often talk about the old TV broadcasts that have been lost, and there's some alien civilization gets very interested in an old television program and is able to tell us some things about it that we didn't know. And you could call that an extraterrestrial fossil. But suppose we wanted to take this information that's been thermalized and get enough of it back so that we can answer actual questions that we care about the Earth. That means getting a majority of it back, and that means a severe global warming problem. I mean, I guess you can say it's not so much a warming problem, because if you put this mirror on, it would also keep the sunlight out. So The real problem is the Earth would suffer heat death. It would come to thermal equilibrium, which I'll talk about a little later. But let's look at this randomizing dynamics in more detail in the specific case. So let's say we're talking about one of these raindrops, and it originates in some quantum and thermal fluctuation, and the thermal fluctuation ultimately is a quantum fluctuation. It does yet not fall in a superposition of places. Everybody who is there will agree where it fell. And as long as the drop exists, or its crater, or the people who remember seeing it, they'll all agree. And the drop itself will reflect a lot of replicas in terms of light that reflects off it and goes off into space. And it fulfills this classicality criterion of quantum span. However, unless the crater is lucky enough to get fossilized, which can only happen to a minority of information, it'll be washed away. And the sort of the terrestrial degrees of freedom that record where this is will be gone. And the new optical replicas will cease, and the old ones will escape into space. So it looked like the classical information of where it formerly was is out in space, but no longer on the Earth. And now, but let's think about this in a more Church of the Larger Hilbert space way. What that's saying really is that the drop that may fall in one of two locations actually is always a pure state. It falls in an entangled combination of the two locations. That is, a bunch of terrestrial observers thinking that it's on the left, and the photon that's reflected off of it thinking it's on the left, plus the similar on the right, divided by the square root of 2. And all these observers will agree with each other, but a God in a sort of more Olympian perspective sees a Schrödinger's cat-like state in which it's a combination of being on the left and on the right. And then let's let it start evaporating. It gets smaller and smaller, and we're emitting more and more optical replicas. And then finally, this state is drops entirely evaporated, and the only information about it is in this celestial information that's all escaped out into space. So the Earth and the sky then are statistically independent, and the sky is in a superposition of states. So really nothing mathematical has happened, but the justification for how people might think about it has sort of changed. At this point, the terrestrial observers have no reason to say that one of these alternatives is more real than the other. And they can say that both outcomes are equally real, even though while it was still on the Earth, they would all agree that it was on the left. And then you might say in another branch of the universe or the multiverse in which none of these people are present, they would think it was on the right. So this notion was expressed already by Wheeler, who says the past exists only insofar as it's recorded in the present. Now that's actually much more appealing than the postmodernists who say that the past exists only in the prejudices of the present. And you might say this has entered popular culture. You can go, I didn't buy this thing, but you could get a plaque to be attached to a space of your choosing where nothing particularly happened. Now, of course, back in 1832, people would have agreed that a lot of things happened, but perhaps nothing important enough to be remembered happened. So this is the quantum story on how we can lose information about the past and how information about the future is the probabilism of the future is not a manifestation of ignorance, nor a manifestation of indeterminacy, but rather a manifestation of our limited perspective as subsystems of the universe. Now that's a lot of philosophy. It says here, at least this philosophy that I sympathize with, is that the escaped information still exists, but it's inaccessible to us, and we have little justification for thinking that one alternative happened and the others are unreal. But Rüdiger Schack disagrees strongly with me. He says he would rather believe that Sappho's lost poems are real and had some definite words in them than that the wave function of the universe is real. All right, how about I'll take some questions?
Well, yeah, let's ask him some questions, at least. Yes, please.
So, about how quantum computers are real now?
Oh.
Quantum computers.
Well,
How they are from real quantum computers, like 100-bit quantum computers or something.
well, they've factored 15 so far.
15?
Yeah, the
I know.
quantum computer is factored
15
15.
is still
Yeah.
small.
Yeah. Well, it's everybody likes to say they have a big quantum computer, but to get one that really reliably works, I think is
Like to factorize RSA numbers or something.
No,
Or
that-
far based on reality.
we don't know how soon that'll happen. I think it'll happen
That's
in the
good.
next 20 years maybe, but not right away.
If you are saying maybe that means
Yeah, it's there are certainly it's as if you can demonstrate pretty good quantum information processing on the scale of a few qubits up to a dozen or so. But to control much larger ones involves good quantum error correcting codes and getting everything, both the hardware and the software, working very well. And it looks like it's a big engineering challenge, but not an insurmountable one. I often compare it to fusion power. Everybody knows that it's possible in principle, but to make it worthwhile technologically has been taking many decades. It still hasn't happened.
Yes, yeah, another question.
Many years ago, I walked around Mount Rainier, close to Seattle, and it was a beautiful summer day, and there was always a little cloud just on top of the mountain, of the volcano. But if you looked a little bit closer, you could see that the cloud was always forming on this eastern side, so on the western side, close to the shore, and dissolving a little later. So was there just a cloud all these hours I was walking around, or was something else going on? So for me, this was a very sort of Buddhist example of reality.
This is the best question I've ever gotten after this talk. Now, from a meteorological point of view, I think what happened is that the air was coming from the west, rising over the mountain, cooling because of the adiabatic expansion. It formed a cloud of water vapor droplets, and then the air went down, and those droplets then re-evaporated. So it was the same cloud made out of different droplets.
Yeah.
It's not very different from saying that the water in the river is the same river but different water.
Yeah.
I think that's what was happening. Yeah.
Yeah, but also, what about information about this cloud?
Oh, that I think that was a good example
Whole system?
of escaped information. That is, if you went up there into the cloud with a tower or an airplane, you could see individual droplets. They would be classical. That is, they could observe their position without disturbing it very much in principle. But then, when they evaporated again, that information would have gotten left in dust grains and air molecules, which then eventually would have escaped into space because it lacked a
Okay, but people tell us that the molecules in our body are replaced by other molecules every 7 years altogether. Maybe this is half time or whatever, but clearly there's just molecules. Matter is coming in and going out, and still we feel that I'm still the same person that 14 years ago, more or less.
I think that's the same reason that if I take some of my favorite old computer programs that I used to run on DOS, I can run them on Windows XP on a totally different computer, and yet it feels like the same program.
Yeah.
I don't think we depend on the identity of our atoms.
So where's identity? in information.
I don't think it's in the matter. I think it's in the information.
Yeah.
Yeah.
Okay, yes.
I just wanted to comment on one of your suggestions of how to keep information for very long, and they said make a lot of copies and store into some another permanent place. And I would say that it is better to and actually necessary to perform some kind of active error correction. Then you can keep it really long time. But if you do it like this, then if you just keep a copy somewhere, it will degenerate in some constant time.
I think that's there's things to be said on both sides of that. The only argument I could raise against that is that the active error correction cannot last any longer than the mechanism that does the active error correction. So you are presuming some stability for that, and that has almost more to do with cosmology than with information theory. But you can also say that the oldest, let's take some example of very old information. Probably the oldest geological information is several billion years old. But that's a minority that lies fossilized in the interiors of continents that haven't been melted for a long time. And that is not replicated very much. The stuff that's replicated very much is some pretty old information, which is the history of magnetization reversals. And that is, well, I guess that's recorded in these old rocks also. And that, in a sense, is a redundant recording in many parts of the Earth. But if we speak about human culture, then I think your argument is correct. Not only human culture, but biological structures. That the oldest information about, let's say, human language is older than the oldest artifacts of, well, I don't know, older than the pyramids. It's hard to say, because some of these artifacts are pretty old too.
You didn't speak a lot about the private classical information. I mean, you you were speculating on this, basically this global CCTV,
Yeah.
which is very public because we also because we replicate many times. So do you have any recommendations on how I should store my secrets?
Oh.
If I want them to be classical, obviously. I mean, I cannot have quantum information, so since it's classical.
Well, see, there's this paradox quantumly. If you want a perfect quantum secret, you have an entangled state in which the information that you store then has no definite value. There's just a correlation without the information. So what you say is, well, I want to store some information in some very small number of copies that only a few people know about. But I think practically there's the paradox. If you store it in too few number of copies, it's in danger of being forgotten. And if you store it in too many, it's in danger of becoming public. So I don't know if there's a mathematical explanation for that, but certainly there's a social explanation. If you don't tell very many people, like if somebody told me a secret, I would just probably forget it, and that would be the end of the secret.
But reliable coding doesn't necessarily have to be a repetition code, right?
Yeah. Right. Okay. So you're saying you don't have to spread it out very much in order to make it, yeah. But how does that concern with? I mean, how if you? Yeah, I guess that's very much an example of secret sharing, where we can pretty much adjust it, the threshold, to whatever we want. That is, the secret is recoverable from 7 of the people, but not from any 6. So you can pretty much decide. I guess that's the answer to that question.